Good afternoon, everyone. Thank you for giving me an opportunity to speak at ACCU once again. Today, we are going to talk about functional tools in modern C++ and what new capabilities we have in the standard C++. I'm Sumant and I work at LinkedIn. This is the week of CPPCon. So I went to CPPCon Twitter channel to figure out what I have been missing. So earlier this week, announcement was made that Dr. Stroustrup won the Faraday Medal. That's kind of neat for his contributions in C++. Who knew that Herb could play piano so beautifully? I probably missed on that delicious cake in the middle. On a little more technical note, I found out a really intriguing tweet about how to detect whether a type is a function or not. That's a neat little trick I would suggest you to check out. There's a lot of interesting technical stuff being shared at the moment, even on the Twitter channel. So I have done some bit of work in C++. I've been blogging C++ truths since 2005. I have a new blog called Coditation. It is more about big data. I've written a wiki book on C++ called More C++ Idioms. And through some of those publications as well as presentations, I've been awarded the Microsoft C++ MVP award as well. So today we're going to talk about functional programming. Most of the examples in my talk, I picked them up from, I've been reviewing this book called Functional Programming in C++ by Manning. And it's a kind of little, it's kind of good introduction, good segue into functional programming. It's a good book from beginners to intermediate programmers to learn how to do better functional programming in C++. The examples that I'm going to pick up here may or may not, they are from the book, but my opinion may not be the same as that of the author. So let's talk about sum types and pattern matching. So sum types is a fancy way of saying discriminated union. So you have a union and you can have multiple types in them. Exactly, one of them is active at a time. And you have an integer value that determines which branch, which type is active at the moment. And pattern matching is a way of writing or executing code based on whichever active branch of the type there is at the moment. So pattern matching takes one or more branches. So let's look at how we can model a domain model, for instance, a game of tennis using sum types, and that would be stud variant in case of C++. The states of a tennis game are normal score. So these are numeric values from 0, 15, 30, and 40. And deuce score. So deuce score is where both players have the same value, 40 each, 40 specifically. Advantage score is when one of the players scores and the other player has scored 40. And game complete score is, of course, the same player scores one more time and you get the player wins the game. So that's essentially how these are four independent states in which a game can be in. So we'll use this example to motivate how variants could be used, and we'll compare this with inheritance approach of modeling alternatives. That would be, of course, motivated by the object-oriented programming principles. So a game state, here is how it will look like. Normal score has player P1, P2, and scores for both players. Both are integers. A deuce score, we assume that it is 40 all. So we don't keep the score, it's just player P1 and P2. Advantage score is we only need to know who is leading and who is lagging. And game complete score is just winner, whoever is the loser, and what is the score of the loser at the point when the game finished. These types are completely independent. They don't have any relationship with each other at the moment. So we have to put them together so that all of them together can model game state. And the way to do that, the syntax for doing that in C++ would be to write stud variant, and we put together all those types, and that gives us a game state. So one of the states is going to be valid at a time, and that's how we create them. Okay, so game state. So what can we do with such a game state? Let's see if we can print it out, whatever is the active branch in it. So at the bottom here, we have a output stream operator, that takes a game state and does a stud visit on on the game state, and we pass in a newly constructed game state printer. The stud visit is something new that C++ has added to work with variant, and it's essentially an implementation of visitor pattern. And game state printer is a visitor in this case, and it must be aware of all the possible variants that the type can be in. For instance, the the first one is normal score, and a normal score, we just print them out. In this case, this is just a printer, so there is nothing fancy about that. It has to understand all the four cases, and due score, advantage score, and game complete score. So a stud visit calls these functions based on whatever is the active branch. Note that the integer to determine which active branch is there is not the detail has not been exposed. So that's the job of stud visit and stud variant, to hide that complexity away. This is very much like a pattern matching, because depending upon the active branch, the right function will be called automatically by stud visit. So this is kind of really neat. The only difference here is that it is library powered. This is not a first class capability in in the language. But then what happens when you miss a case or something like that? Stud visit simply spews blood on your face. This is stud visit's way of saying that, hey, you are missing a single case, or maybe two. It is it is so annoying, it is so arrogant that I don't think a library way of implementing pattern matching is the right way to do. So I think C++ Standards Committee is considering first class pattern matching, which would be much more polite in telling you that, hey, you are simply missing a case, and not have such a page full of errors for you. We can get fancier with stud visit. So instead of passing a named class, earlier case it was game state printer, we can actually pass in a collection of lambdas together, each lambda for each type case. So here it is. The first case is normal score. There is no change in implementation, and we have four lambdas for one case each: due score, advantage score, game complete score. Look that they are all overloaded, so they are all being passed to a fancy thing called overloaded, which is, by the way, not provided in the C++ standard. This is something you have to write to if you want to use the stud visit and overloaded lambdas in this style. But this is kind of neat. You don't have to exit out of your context. You can just write all the cases in a lambda, and the side effect of that is that the behavior that you need is all encapsulated in a single function. In this case, the OStream operator, and that's the added benefit. So how does the overloaded really work? So it is essentially inheriting from lambdas, because lambda is essentially a type that is being generated by C++ compiler. So overloaded is inheriting from all of them, and it does its that there is some specific syntax that you have to handle. Like you have to say using operator function call, because all those functions should be available in the scope right here. And then there is an explicit overloaded constructor to pass those values back to the overloaded lambdas. There is one more quirk here, which is user defined deduction guides. So you don't have to actually write the overloaded constructor. You can actually instruct C++ to say, look, if you see this syntax like overloaded followed by some set of types and the values, then just construct an overloaded type of like that. So this is a brand new feature in C++ called user defined deduction guides. This is the same feature that powers that you don't have to type in template arguments. For instance, you are using a pair, then you don't have to pass in the types for the C++ class template. C++ class template arguments are automatically deduced, just like the function template arguments are deduced today. So this is kind of a neat feature. I was rather surprised to see this user-defined deduction guide. It's kind of sneaky way to enable that succinctness, which is kind of neat. But over here, it's been used in yeah, it's kind of interesting. I think I'll just stop at that. I briefly mentioned earlier that one effect of using pattern matching is that the entire algorithm gets concentrated into a single function, and it's all in one site. So let's look at a more complicated example of that in our tennis game state example. And here we want to compute, given a game state, the next game state depending upon which player scored. So the function is called next, and it takes an existing game state and it returns a new game state depending upon the player who scored. And again, we will implement this using studVisit and a set of overloaded lambdas. So here is the first case, which is if the existing state is deuce, then depending upon who scored, you return an advantage score, and you put the right player in place. For each such game state, the algorithm goes and adds individual cases. So this is for deuce. We'll go ahead and add a case for a normal score. That's going to be a little bit more complicated. The others are from advantage score, you can someone can win, and from game complete score, it is just an illegal state. And on the right hand side here, this is the much bigger part, which is the normal score, and whoever scores, depending upon that, we return a new game state. So how many of you think that having an entire algorithm together in one function is an important benefit for a software developer? Can I see some hands? Okay, so sounds like a few people in the room would like to see it this way. And then alternative here is I have not exactly shown you, but which is the inheritance way, where the algorithm, the next function, will get distributed in multiple classes and potentially multiple files. So in order to understand the algorithm, you have to open multiple files. So how many of you think that kind of style is actually preferable? Okay, again a few hands went up, so I guess others cannot really make up the mind. And actually I fall into that category, that I'm not exactly convinced which one is the which one do I really like. Let's look at an object-oriented decomposition of this problem. So on left hand side we have game state, and game state has a unique pointer to the game state impl, and game state impl is essentially a interface, has a pure virtual next method and a pure virtual destructor. So each on the right hand side, each concrete state, normal score, deuce score, implements this interface, and each one must implement next. So how to go from the given state, from this to the next state given the player that scored. So that must be implemented. Note that the state is shared in the player P1 P2 state is only in game state impl, which all the concrete classes can inherit, and anything that is missing can be added in individual classes. So sharing state becomes much easier with inheritance, I think. Let's imagine we want to answer questions that are common to all game states. For instance, who is serving? This is a state that must be maintained in each game state, and it really doesn't change from one game state to another. Let's imagine fastest serve speed. That also, in a given game, doesn't really change from the game state. So this is something that we can capture easily with game state impl, and because it is inheritance, by definition, the state and the functions as well are inherited into the child classes. So it becomes rather convenient to share state in this fashion. And the last, one more piece that I want to talk about is last state. So one game state is returns what was the last game state, and we may want to like go through the entire history of a match or whatnot and analyze that. And so it essentially, so think of it sort of a linked list that goes back in time. We'll come back to that a little later. So let's compare the state aspect with stud variant. In this case, now each independent game state needs to have the state for the common needs to have the common state. For instance, serving player, it's repeated in all four independent states. Now, similarly, a function to return that state, like who is serving, is also must be declared in each game state. So I think there is a little bit of repetition in case of stud variant, and this is not the only way to decompose a game of tennis into four states. There may be other refactorings possible where these common things like serving player, fastest speed, those kind of things can be extracted out of the truly variant part, which is the score. So I'm not saying this is the final word on the composition, but let's imagine for a moment this is how we do it. You will realize that extracting the information though becomes slightly more convoluted. For instance, in case of a variant, to find out who is serving, we have to call stud visit, because that's the way to do pattern matching in C++ as a library. And we have to pass in a lambda. That lambda takes an auto parameter, auto s, because it could be any of the possible alternatives here. And inside that lambda, we have to call the real function, which is who is serving. So this becomes a little bit of ceremony, and compare that with object-oriented method, where we simply call state dot who is serving. So because of the language level support of object-oriented programming, I think it is very hard to beat that kind of succinctness. There is too much ceremony going on for simply extracting a single bit of value. And I think while doing pattern matching in C++, this is something you have to keep in mind. Now let's look at recursive game state, a recursive variant. This is the case when we want to find out the last game state from a given game state. Now imagine we want to go back the entire match. Can a stud variant contain itself? Actually, it cannot. It is not possible unless you use something called recursive wrapper. And recursive wrapper, unfortunately, is not included in C++17. It is available in Boost libraries. Of course, you have to use Boost recursive wrapper with Boost variant. You cannot mix standard and Boost together, as far as I know. So this is a bummer, really, because this really means a stud container is simply a stud variant is simply a container, and it really doesn't serve as an abstraction, because you cannot put together two variants and one that contains itself. You cannot really do that. It is pretty much not algebraic. Compare that with, say, common functional programming languages like Scala or F Sharp or even Haskell, that some types are a really powerful way to abstract data. They are called algebraic data types. You can take smaller pieces and create a larger one without changing the interface. It's essentially composite design pattern. You cannot do that alone. You cannot do that with stud variant alone. And um, with recursive wrapper, you also kind of have to bring in dynamic allocation. So you lose the nice value semantics of variant, but that's just a downside of variant, dynamic allocation or dynamic abstraction. Okay, so moving on to stud variant also disables fluent interfaces. So I really come to like this style of writing functions. The state dot get last state, get fastest serve speed at the bottom there. You just chain these functions one after another, and you can just read this code as text. But you cannot really do that with variant. There is a lot of ceremony. You have to pass in multiple stud visit, multiple lambdas, and it becomes not easy to read. So this is something I would watch out for before opting into stud variant. Now we talked about briefly that with variant and we can combine inheritance with some types because C++ allows us to do it in a multi-paradigm fashion. So here is a shared game state and has a single implementation who is serving and also remembers the player name or player in that case. And this game state is a V2 variant, and the V2 variants contain the individual they inherit, but they do not implement, say, the next function which is virtual. So I think that is a nice way to combine both. So recapping the differences between stud variant and inheritance, you can go through this as you find time, but the main things are we talked about value semantics and then reference semantics. Also algorithm tends to be in one place with stud variant, and it is library supported, whereas inheritance is language supported, so it feels a little bit nicer. And I think the main difference is inheritance allows you to create abstractions, but stud variant alone doesn't really let you create abstraction as such. It's just a container. Switching gears now, let's talk about immutability. In functional programming, immutability is very important. C++ happens to be a unique language that has compile time support for checking immutability of a value, and it is provided via const functions or const variables. So consider this example. We have struct x and a function bar. It's not a const function. And in struct y, we have a pointer to x, and function foo calls, which is a const function, calls bar on pointer of x. So a const function is calling a non-const function. And down below we have a const value of y, and it is calling foo. So what do you think happens here? Is x.bar called or not, or whether this is a compile time error? As it turns out, it is actually works. It's actually fine code because const is shallow. It only applies to the pointer. We can fix that using something called propagate const. A propagate const is essentially a wrapper on top of a pointer, and depending upon the context in which propagate const is used, it is either treated as a const or not. So here we have to add a const function in x, and the x pointer is wrapped in propagate const. So now a const y, when it calls foo function, within that x pointer, because it is wrapped in a propagate const, it acts as if it is a pointing to a constant object, and hence to call a bar function we have to have a const overloaded version of it available in x. So now the entire program guarantees that because y is a const object, all the functions that are called within that, because and of course combined with propagate const, it is constant. So the y dot foo is guaranteed to be a non-mutating operation. Of course, you can add exceptions using mutable and all, but I thought this is kind of a neat feature that we have now. So propagate const is available in library fundamentals TS v2, and you can put together a shared pointer or unique pointer, whichever way you like. And if you call get on it, depending upon whether it is in const or not, you will either get a const qualified pointer or not. And so the same propagate const can be used, same object can be used in two different contexts depending upon how the container is there. So of course dereferencing is possible. You can also get the underlying pointer and it will maintain the constness of it via get underlying. An interesting thing that I saw that once you use propagate const, your class is no longer copy assignable, and that's because even in basic C++ language, you cannot assign a const pointer to a non-const pointer because that simply discards the qualifiers. That's not allowed because that assignment will allow later on a const object to change, and that's why unless you do a const cast, such a assignment is not allowed. So you have to opt in such behavior. For the same reasons, a a const share a const propagate const object cannot be assigned to a non-const one, and hence your class becomes non-copy assignable. However, you can always move, so it maintains the reference semantics of the pointer, so you can always steal the guts of the on the right hand side, copy the pointer over, and continue working that way. So in that sense, propagate const kind of works nicely with rest of the language, I feel. Switching gears one more time, we're going to talk about mutable temporaries in this section. So in C++, temporaries have always been mutable. You can assign them to a const reference, but that doesn't make then in that case they are immutable. But by default, temporaries are mutable, and in C++ 17 now you have a way to systematically modify them when there is an opportunity. So we will talk in this section. We'll also talk about what might be a reason to use std move on star this, and you might guess where this is heading now. So here's an example of where a lot of temporaries are generated, and you might want to modify them. So a name parameter idiom is useful when you want to pass in multiple arguments to a function or a constructor, and they happen to be of the same type. For instance, say 5 to 10 string parameters. If you ever done SSL programming, you might know that you have to pass in like up to 10 or so string arguments, and it becomes really hard to read that code. So name parameter idiom allows you to arbitrarily reorder them because they are named, like set server localhost, set protocol, HTTPS, and these functions can be chained. So configs class in this case returns itself in these functions, so that you build a state of the configurations, and in an object you start with an empty object, you put state in it, and you pass that into the constructor or a function. So if you want to take immutability seriously, then perhaps we should try to keep the configs object also immutable. And in that case, the name parameter idiom becomes rather interesting. So I think on the next slide, I have an example where the set server and set protocol functions are immutable, and therefore they do not change the original configs object, but they create a temporary version of this, and that temporary is modified with a with whatever the value that is passed in, and you return the temporary. Note that the functions are const. So now when the empty configs object is created and set server is called, it returns a new object that has the localhost value, and so on. And set protocol returns another object that has HTTPS and localhost in it. It does not change the original object at all. There is, however, a downside of this, because each function adds a tiny bit of state and it causes number of copies. So for instance, if we run this program, the configs object is created 3 times and destroyed 3 times. And each time a bunch of string objects are created and destroyed. So this is probably not a great style. So can we actually avoid that? As it turns out, yes, you can in fact do that. So we will have, in this particular case, a const function. This is same as before. Set server and set protocol are same as before, but they will only work on const objects. And note what I added. So in the code in blue is, at the end you will see a ampersand at the end. So we overloaded set server and set protocol functions with R value references. So this is a R value reference qualified overloaded function. So whenever set server and set protocol is called on a R value that's a temporary, this function will be called. And to disambiguate that from a regular and L value object, and calling a function on that would be a little ampersand. If you note up there is a little ampersand up there. So that disambiguates between two different contexts. Now note what's the implementation in blue is doing. It returns star this. All the functions are returning configs by value. So each time these functions are called, a new object of configs is created. If configs object is a const one, then the first 2 functions will be called and a temporary copy will be made, and then a temporary of configs object is created, and from that point onwards the functions in blue will be called, because an R value reference, because the bottom functions are R value reference qualified. So if we take this program and run it, what actually happens is none of that I said was helpful in reducing the number of constructors and destructors called for the configs object. So what's really happening? The trick is in understanding that even if we have R value reference qualified functions, we are returning by value from them. So the blue functions return by value. So even if star this is an R value reference, inside that function it is still an N value. So when we return an L value by value, then in that case the language calls a constructor, and hence we see the copy constructor being called for configs object twice for 2 functions. So the trick is returning an R value reference itself, and therefore we change the return type to configs ref, which is an R value reference, and inside the implementation we return std_mu of star this. So this is simply a cast at this point. So the star this, which is actually a L value, but because we know we are inside a R value reference qualified function, the blue functions, we can safely cast it to a R value reference configs ampersand. And therefore when we make this change, because it's simply a cast, no more new objects of configs type are created and therefore no more of them are destroyed. And we can optimize, we can still start with a temporary object and make modifications to it without creating any extra copies of the object. And that's basically it, all I have to say today. Thank you for coming in and listening to this talk. If you have any questions, let me know. Thanks.